Have you ever wondered how LEDs, or light emitting diodes, have become an integral part of our daily lives? Let's start at the beginning. LEDs have a rich history dating back to the early 20th century when a British inventor named H.J. Round discovered electroluminescence. However, it wasn't until the 60s that the first practical LED was developed by an engineer at General Electric. The basic principle of operation of an LED is simple yet fascinating. When an electric current is applied, it excites the electrons in a semiconductor chip, and when these electrons return to their normal state, they emit light. This is quite different from traditional lighting technologies like incandescent and fluorescent lights, which produce light through heat or gas discharge respectively. Now, compared to these traditional light sources, LEDs offer several advantages. They're more energy efficient, longer lasting, and compact. They also turn on instantly and can be dimmed to suit our needs. Plus, they're environmentally friendly since they don't contain mercury like some other light sources. However, LEDs are not without their limitations. They can be more expensive up front, although they typically pay for themselves in energy savings over time. They also require more precise current and heat management than traditional light sources, making their design a bit more complex. But what's truly amazing about LEDs isn't just their efficiency or longevity, it's their versatility. LEDs can emit light of nearly any color without the need for color filters, unlike traditional lighting technologies. This ability, combined with their compact size, has opened up a world of possibilities, from the screens of our smartphones and TVs to the lights in our homes and even in innovative fields like horticulture and medical therapy. So the journey of LEDs from a simple indicator light to the technology powering our screens and lighting our homes is truly remarkable. Now, you may be curious about the science that makes LEDs possible. Let's delve into the core of LED physics, starting with the fundamentals of semiconductor physics. Semiconductors, as the name suggests, are materials that have properties between conductors and insulators. They don't conduct electricity as well as metals, but they're not as resistant as insulators either. The beauty of semiconductors is that their conductivity can be controlled, making them perfect for electronic devices like LEDs. Now let's move on to the p-n junction theory. In a nutshell, a p-n junction is a boundary or interface between two types of semiconductor material, p-type and n-type, inside a single crystal of semiconductor. The junction only allows current to pass in one direction, creating what we know as diodes. When a voltage is applied to the diode, it pushes the electrons from the n-type material towards the p-type. At the same time, it pushes the holes or vacant electron spots in the opposite direction. This brings us to the concept of electron-hole recombination. As the electrons move across the junction from the n-type material, they fill the holes in the p-type material. This process, known as recombination, releases energy in the form of photons, particles of light. The color of the light depends on the amount of energy released, which is where the band gap comes into play. The band gap is essentially the energy difference between the conduction band, where free electrons exist, and the valence band, where the electrons are bound to the atoms. The size of the band gap determines the energy of the photons and hence the color of the light emitted. For instance, materials with a larger band gap emit blue or white light, while those with a smaller band gap emit red or infrared light. Lastly, we have quantum efficiency, a measure of how efficiently the LED converts electrical energy into light. It's influenced by factors such as the quality of the semiconductor material and the design of the LED itself. In essence, the color and efficiency of an LED are determined by the materials used and their electronic properties. But how does an LED emit light? A fascinating question indeed. The answer lies in the world of photonics and the unique optical characteristics of LEDs. Let's begin by discussing photon generation. When an electron and a hole combine in the semiconductor material of an LED, they annihilate each other, producing a quantum of light or a photon. This phenomenon is known as electron-hole recombination. The energy of the emitted photon corresponds to the difference in energy levels between the electron and hole, which determines the color of the light we see. Now, this light emission doesn't happen randomly, it follows specific mechanisms. The most common one is spontaneous emission, where an electron spontaneously drops from a higher energy level to a lower one, emitting a photon in the process. This is the primary mechanism at work in most LEDs. Moving on, let's talk about optical properties. These include spectrum, coherence, and polarization. The spectrum of an LED light source is determined by the energy band gap of the semiconductor material. Coherence refers to the phase relationship between different points in the same wave. And in LEDs, light is typically partially coherent. Polarization, on the other hand, is the orientation of the oscillations in the light wave, and in LEDs, light is usually unpolarized. Designing an LED involves optimizing these properties to maximize light output and efficiency. This is achieved through various means, such as tweaking the shape and material of the LED chip or incorporating structures that direct light out of the device more efficiently. A variety of materials are used in LED construction, each with its own unique optical properties. From gallium arsenide to indium gallium nitride and even organic materials, the choice of material greatly impacts the performance and color of the emitted light. In the end, it all comes down to how well we can manipulate these materials and structures to optimize light output and efficiency. It's truly a marvelous blend of physics, material science, and engineering. LEDs are not just about optics, they also have unique electrical characteristics. To understand how LEDs work, it's important to first get a grip on their IV or current voltage characteristics. Simply put, this is a graph that shows the relationship between the current that flows through an LED and the voltage across it. Unlike traditional light bulbs, LEDs don't have a linear IV characteristic. Instead, they exhibit a curve that reveals a critical point, the turn-on voltage. Below this voltage, no significant current flows, and the LED doesn't emit light. But once we cross this threshold, the current and the light output increase rapidly with voltage. Now let's turn up the heat and talk about thermal management. LEDs may run cooler than incandescent bulbs, but they still produce heat. And too much heat can degrade the LED's performance and shorten its lifespan. That's why effective thermal management is crucial. The most common approach is to use a heat sink, which absorbs and dissipates the heat generated by the LED. Moving on, let's illuminate the topic of drive circuits. LEDs need a constant current source to operate optimally. So LED drive circuits are designed to provide this constant current, regardless of changes in input voltage or variations in LED forward voltage. There are many ways to design these circuits, from simple resistor-based designs to more complex switch-mode power supply designs. Finally, let's dim the lights and discuss dimming techniques. Unlike incandescent bulbs, you can't simply reduce the voltage to dim an LED. Instead, you can use techniques like pulse width modulation, where the LED is turned on and off at a high frequency. The average light output is reduced, creating the illusion of dimming. In conclusion, LEDs require careful electrical management to ensure they operate efficiently and have a long lifespan. So whether you're designing a new LED product or just installing some LED lights at home, it's important to understand these electrical characteristics and how to manage them. With such fascinating technology, where do we apply LEDs? The answer is just about everywhere. LEDs have found their way into our homes, offices, and even our cities, transforming the way we illuminate our world. In residential and commercial settings, LED lighting solutions have become the norm. They offer a gamut of benefits over traditional lighting sources. LEDs provide superior brightness and color accuracy, making them ideal for everything from task lighting in your home office to mood lighting in your favorite restaurant. Their long lifespan and low energy consumption also make them a cost-effective choice. An LED bulb lasts approximately 25 times longer than a traditional incandescent bulb. This means fewer replacements and more savings in the long run. Plus, they consume about 75% less energy, reducing both your electricity bill and your carbon footprint. LEDs aren't just practical, they're also a designer's dream. Their compact size and flexible design allow for architectural and aesthetic applications that were once impossible. Picture an iconic skyscraper, its facade glowing with dynamic, color-changing LED lights. Or imagine a minimalist living room, its ambiance defined by recessed LED lighting. But the potential applications of LEDs extend far beyond aesthetics. They are paving the way for smart lighting systems that integrate with the Internet of Things. These systems can adapt to our habits, preferences, and even our moods. For instance, smart LED lighting can simulate sunrise to gently wake you up or dim the lights when it's time to wind down for bed. Furthermore, these smart systems offer energy-saving modes and remote control functionality, giving us more control over our energy consumption. And as we move towards a more sustainable future, every bit of energy saved counts. The versatility and efficiency of LEDs have revolutionized the lighting industry and opened up new possibilities for smart and sustainable solutions. As we continue to explore and innovate, who knows what the future of LED lighting holds? But one thing is for certain, it's going to be bright. So, what does the future hold for LEDs? Now that's an illuminating question. The future of LED technology is brimming with potential, lit up by advancements in nanotechnology and quantum dots. These tiny particles, smaller than a billionth of a meter, are being used to enhance the color and brightness of LED displays. Imagine watching your favorite movie with colors so vibrant they leap off the screen. In the same vein, we're seeing the rise of organic LEDs, or OLEDs. Unlike traditional LEDs, which require a backlight, OLEDs emit light when an electric current is applied. This allows for thinner, lighter displays with truly deep blacks. You might have already seen OLEDs in action if you've got a high-end smartphone or television. Of course, the journey to brighter, more efficient LEDs isn't without its challenges. Material science and engineering are playing crucial roles in overcoming these hurdles. Researchers are constantly seeking new materials that can improve the efficiency and longevity of LEDs. But perhaps the most exciting aspect of the future of LEDs lies in their potential to revolutionize our global energy scenarios. LEDs are incredibly energy efficient compared to traditional light sources, and as the technology improves, they could play a significant role in reducing our carbon footprint. The future of LEDs looks bright with new technologies and applications on the horizon. So let's keep our eyes open and watch the future unfold, one light at a time. So, what have we learned about LEDs today? Well, we've journeyed from the basic principles of LEDs, understanding their operation, and comparing them to traditional lighting technologies. We've delved into the physics behind these fascinating devices, exploring semiconductor fundamentals, electron-hole recombination, and the role of band gap in determining LED color. We've also examined the photonics and optical characteristics of LEDs, learning about photon generation and emission mechanisms and how LED design can optimize light output and efficiency. On the electrical side, we've discussed LED IV characteristics, the importance of thermal management, and various drive circuit designs. We've seen how LEDs are revolutionizing residential and commercial lighting, and even making waves in advanced applications like display technology, medical therapy, and agricultural growth. We've looked ahead to the future of LEDs, where nanotechnology, quantum dots, and organic LEDs promise to push the boundaries of what's possible. But perhaps most importantly, we've seen how the humble LED is much more than just a light source. It's a symbol of our technological progress and a beacon for a sustainable future. From energy savings and sustainability to smart lighting systems and IoT integration, LEDs are set to play a key role in our lives. As we continue to innovate and explore new applications, who knows what exciting developments are just around the corner? Remember, the humble LED is more than just a source of light. It's a symbol of our technological progress and a beacon for a sustainable future.